Hello, we're ready to talk about our third conic section, the hyperbola. You've had some experience graphing hyperbolas centered at the origin, so let's take a quick review of that because then we're going to focus on looking at hyperbolas that are not centered at the origin. So both of these are the standard forms for a hyperbola whose center is 0, 0, and the hyperbola that has the curves opening left and right will have its vertices. Remember, those are the points that we know on the curve. Its vertices will lie on the x-axis. Okay, and we call that axis that connects the vertices the transverse axis. Also, we say the foci will lie on that transverse axis as well, inside the curves. Okay, and we have that same situation that with our ellipses, that the distance from the center to each vertex is A, and the distance from the center to each focus is C. Okay. Now, when we look at what B represents in a hyperbola, we can't really see it in the graph. What we use B for is to construct our rectangle. It gives us the other dimension of our rectangle that we can use to draw our asymptotes that help us draw accurate curves, or our asymptotes are the lines that our curves approach. Okay, so what's the difference between these two standard forms? Well, over here, once again, my vertices are the points on the curves. They're on the y-axis. So we say it has a vertical transverse axis. And my foci would be located farther out on the transverse axis. Okay. So how do we know if it's oriented left and right or up and down? Well, it depends on whatever variable is first. Because the main difference between the equation of a hyperbola and an ellipse is the subtraction. Okay, so one of the terms, either the x squared or the y squared term, is negative. So we always like to write the term that is positive first. We don't like that negative sign hanging out front. So whatever variable comes in the top of the first fraction tells me the orientation. Notice how the denominator in both cases, a is always below, or is always in the denominator of the first fraction. Okay, so a squared is always first, but a squared is not always larger. With an ellipse, it is, but not with a hyperbola. In a hyperbola, a squared and b squared can be equal. A squared can be larger than b squared, or b squared can be larger than a squared. So we got lots of options there. Okay, so let's look at our standard form if we talk about the center being at another point, which we will also refer to as HK. All right, so we've got our two standard forms down here. So pretty much the only thing that we've changed now is we've replaced x with x minus h and y with y minus k. The one place you have to be really careful here is when the transverse axis is vertical and the curves open up and down, the y comes first. So when you give the coordinates of the center, you have to make sure that you're starting with h first and then k. So you got to pay attention there. And we can see the relationship between a, b, and c. Now, to find c squared, we add a squared and b squared. And we're also going to give the equations of the asymptotes. So you can see we have two different forms for our equations. It just depends. Different textbooks, different places write them two different ways. And some of our My Math Lab homework problems are from a different textbook. So one textbook uses the first version and one textbook uses the second version. So you just have to keep your eye out for which one they are putting the asymptotes in terms of. But notice that basically this standard form equation for the asymptote comes from the point slope form. y minus y sub 1 equals m times x minus x sub 1. So basically it's saying you can write the equation of a line if you know a point on the line, which we do. The only point on the asymptote that we know is the center point. And then you must know the slope, which we will get the slope. The slope comes from a and b, so it's either a over b or b over a, depending upon the orientation. Okay, so we'll write some equations of asymptotes. But basically, you use the same, you use a, b, and c for the same things. We're just starting at a different center point as a point of reference. So let's look at one that is in standard form already, and it has been shifted off of so that its center is no longer at the origin. So here's our equation, y squared over 25 minus x plus 3 squared over 4. So I can see that I have a minus here. That's why we have a hyperbola. Okay. Notice how in the first fraction, I have just a y squared. Okay, there's no plus or minus. So remember, if it's just a y squared, then that means it's the same thing as y minus 0 squared. So that means the y coordinate of the center is 0. Okay, so here's where they're switched. You have to be careful. Whatever here is being subtracted from x, remember, results in the x coordinate of the center, or h. So we can think of x plus 3 as x minus negative 3 squared. So my h is negative 3 and my k is 0. So the center has coordinates negative 3, 0. So it's only been shifted to the left. Okay, so if I go to I can go ahead and put my center here, negative 3, 0. Now, I need to know the orientation because I need to know which way to go to get to the vertices. So we can get that from our standard form. Whichever variable is first tells me the orientation. The y is first, so that means the transverse axis is vertical like the y-axis, which means my curves open up and down. So I always recommend you draw a little picture for yourself so you remember which direction you're going and where your vertices are located, because these graphs can get quite busy. Okay, so I know I'm going to go up and down a certain number of units to get to the vertices. Well, those units would be whatever a is. So a squared is either 25 or 4. Okay. Well, in a hyperbola, a squared is always the first one, not the larger one, the first one, although 25 is larger now. So a squared is 25, that means a is 5. So that means we are going 5 units up and down to get to each vertex. Okay, so if I want to find the coordinates of my vertices, then I recommend you do not rely on the graph. Come up with the coordinates of the vertices, then plot them and make sure that they appear that they're in the right place. Okay, so because I'm going up and down, I'm changing the y coordinate of the center. So the x coordinate will stay negative 3. I'm taking 0 and I'm adding and subtracting 5. So that's going to give me my vertices. My first vertex is going to be negative 3, 0 plus 5, or 5. And my second vertex is going to be negative 3, 0 minus 5, which is negative 5. So if I plot those 2 points, they should lie on that same vertical line as the center. So negative 3, 5, here's a vertex. And negative 3, negative 5. Here's a vertex. So they appear to be the same distance from the center. The center is the midpoint. Okay, so now I want to draw my curves, but I want to draw them accurately. I don't know, are they really wide curves or are they really narrow curves? I don't know. So that's why we want to use our asymptotes to get accurate looking or accurately shaped curves. Now, there's a couple ways you can do that. You can actually just come up with the equations of the asymptotes and then graph those lines. which is totally fine, but it's fairly tedious. So there's a way of drawing those asymptotes a little more quickly, which is what I like you to do when you're drawing your hyperbolas. It doesn't matter to me if you do it, but you have to draw your asymptotes accurately. Okay, so let's go ahead and do the rectangle method, as I might call it, and then we'll write the equations and make sure that they come out to be the same. So we're going to have our rectangle is going to have the dimensions of whatever the transverse axis is and the conjugate axis. So the conjugate axis is similar to the minor axis, although it's not always the shorter one. But we use the other number, which is b squared. So b squared is 4. So we use b then to help us find the endpoints of the conjugate axis. So if I went up and down to get the vertices, I go left and right to get the endpoints of that conjugate axis. So I'm going to go 2 to the right, and I'm going to go 2 to the left. Okay, those are not actually points. I typically don't even like to draw them as points or draw them in a different color, because what happens is I see students draw the rectangle and then they forget which points, and then they have their curves opening the wrong way. So either make sure you have a picture to refer back to, or you definitely designate that you know which ones are the vertices. Let's talk about our two axes and how it relates to the dimensions of the rectangle. Okay, so if you recall, our transverse axis has a length of 2a. So it's basically the distance between the vertices. So our transverse axis is 2 times 5, or 10. The other axis is called the conjugate axis, which does not really help us with anything. We don't have anything actually on the graph. It just helps us draw our rectangle. But the conjugate axis is 2 times b, and b is 2, so our conjugate axis has a length of 4. So I will be drawing a rectangle that is 4 wide and 10 high. Okay, so it's basically going through these 4 points, and we dash it because it is not actually part of the graph. I'm going to use my drawing tool, but okay, maybe I'll do it on the asymptotes. Okay, so now the asymptotes are the diagonals of that rectangle. So what I recommend you do, so that you keep them at the right slant once you get outside of the rectangle, is what's the slope? So if I'm going to draw my diagonal, I always like to start at the center. And when I start at the center, then I go, to get to the corner over here, I go up 5 and over 2. So basically, that's the slope of my asymptote. Okay, so I'm going up 5, which happens to be A, and then I'm going right 2, which happens to be B. Okay, so fine and dandy, and when I draw in the rectangle, I'm good, but when I get outside the rectangle, I don't want to do this. Okay, so I want to make sure I keep that same slope. That's why I make a note of it, unless I'm using some kind of a straight edge. So I'm going to continue. I'm going to go up 5, right 2, so that I have another point so I can draw it accurately. Other direction, I'm going down 5, left 2, continue that pattern, and there's my first asymptote. Now, when I come up with the equation of this asymptote, I know one thing about it. I know the slope is 5/2. Okay? I don't know the y-intercept. Now, I might be able to tell if my graph is drawn accurately, but a lot of times we cannot tell. But somewhere up here around 7. And it might just be 7. That'd be something we need to look at. Okay, so I do the same thing with my other asymptote, which is going to have the same slope except for it's negative. So I'm going to go down 5, right 2. That one looks pretty bad. Now I got on the thick line. So I'm going to go up 5 and left 2. Oh, come on. Okay, let's see here. This again. Oh my gosh. Okay, there we go. Fight with that thing. So this other asymptote, when I draw this one, I'll put it down here. It's going to have a slope of -5/2, but I don't know what the y-intercept is. Looks like -7. I'm guessing because my center is on the x-axis that they're going to be at the same value, but one's positive, one's negative. Okay, so now I have what I need. I draw my curves. So my curves have to go through the vertex, and then they are going to approach my asymptote, but never touch or cross. Okay, so those are just my guidelines so that I can draw an accurate graph. So there are my two curves of my hyperbola. Get this out of the way a little bit here. Okay, so that's how we can accurately draw our hyperbola using the asymptotes. Okay, now if you didn't construct the rectangle, then you would need to come up with these equations of these two asymptotes, draw them accurately, and then put in your curves. So I guess it's whatever you're more comfortable with. I think most people like the rectangle method. All right, so how do we come up with the equations of those? So we have our standard form that says y minus k, so y minus the y coordinate of the center, because that's the only point we know. It's the only point that we know that's on each asymptote, equals the slope, which we know is b over a, or sorry, I'm sorry, a over b, and then it's x minus h, the x coordinate of the center. Okay. Now, because there's two different slopes, we need to set up two different equations because we're going to have two different slopes, but we also have two different y-intercepts, as we can see over here. So you have to figure them out separately. So let's set them up individually. So I have y minus k, k is 0, equals a over b, which we know is 5/2, times x minus -3, which is x plus 3. Okay, so that's the first form that we could write it in, but because it's 0, we probably would just go to, which is actually the second form, 5/2 x plus 3. Okay, now if you were going to graph them, you would need to go ahead and multiply that out, distribute the 5/2 to actually get the y-intercept. So y equals 5/2 x plus 5/2 times 3 is 15/2. So I know 15/2 is what? Approximately 7.5. So it does not cross at 7, it crosses at 7.5, which is very difficult for us to judge from a graph. Okay, so that's my asymptote up here. So this would be 15/2 or 7.5 is okay because it's a terminating decimal. And that looks, I guess, about where it looks like it crosses right here. Okay, so what do you think the other one's going to be? -7/2. Now, does that always happen? No. So I have, once again, y minus 0 is negative a over b, or 5/2. Times x plus 3. So the only thing you have to really change is the slope and then what you get after you distribute. So this becomes -5/2 x minus 15/2, which is minus 7/2, 7.5. Okay, so that is an option. Just come up with those equations, draw them out accurately, and you've got your curves. Pretty cool. My favorite conic section. All right, now we know from previous experience the equations are not always given to us in the standard form. So we are going to have to put it in standard form. We did this with circles. We did this with ellipses. We are now going to do it with hyperbolas. The hyperbola is just a little bit trickier. There's two places where you have to be very careful. Okay, but we still start out in the same way. First of all, let's make sure this really is a hyperbola. How do we know? Because to me it looks like an ellipse. It has a 9x squared and a 4y squared. We had ellipses just like that. However, what I notice is that one of the x squared or the y squared terms is negative, and in this case, the y squared term is negative. Doesn't matter that they have, we can't judge that, or we can't determine that it's a hyperbola based on the 9 and the 4, because they could both be 9 and be a hyperbola if there's a minus. They could both be 4, so that isn't what tells us that it's a hyperbola. Okay, so go about our business. We want the x terms in descending order together, the y terms together in descending order, and the constant on the other side. So I'm going to do a little rearranging and housekeeping here, just as we did with the ellipses. So I'm going to subtract the 92 and move it to the other side. So that gives me negative 92. Okay, and I'm going to have to factor out those coefficients on the x squared and the y squared terms first so that I can complete the square. So I'm going to factor out the 9 from the x terms. Leave a space to complete the square. Now, here's where you have to be careful. The coefficient on y squared is actually negative 4. So you have to factor out a negative 4. Okay? That means you have to divide both the y terms by negative 4, which is going to change the signs of both of those terms. So you come up with positive y squared minus 4y. So you got to be careful. If I see mistakes, it's just because this gets missed. Which, if that's the only thing that you did wrong, then all it does is mess up your center, but we don't want you to get it wrong. All right, and leave a space. And don't forget you're going to add something to the other side, or add whatever you added to the left to the right. Okay, now we're ready to complete the square. Go to the square here. Go to the coefficient on the x term, take half of it. Half of 8 is 4. 4 squared is 16. So I'm adding 16. But did I really add 16? No, because I factored out a 9, which means if I was going to put it back in general form, I would be distributing that 9. So I would eventually be taking 9 times 16. So that's what I need to add over here on the right, is 9 times 16, which comes out to be 144. All right. Now, half of 4 is 2. 2 squared is 4. Okay, so I'm going to add 4 here. But did I really add 4? No. I added whatever I factored out times 4. Here's where your second tricky part. You factored out a negative 4, you have to multiply by a negative 4. So you're going to add the product of negative 4 and 4, which is negative 16. So technically you're subtracting 16. You could go ahead and write that. All right, so that's the two tricky spots, is with that negative. And now we just go about our business the way we did with ellipses. We factor our perfect square trinomials. And we simplify the right-hand side, which should simplify to 36. We're oh so close to standard form. Okay, so I need the 36 over here on the right to be a 1. So I'm going to divide everything by 36. And then simplify. So here, 9 and 36 have a common factor of 9. Divide that out. So that becomes x plus 4 squared over 4. Here, 4 and 36 have a common factor of 4, so I divide that out, top and bottom, which leaves me with 9 on the bottom, equals 1. And this is my standard form equation of this hyperbola. Okay. So let's go ahead and take a look at this and do another graph. All right. So I have my equation up here. And so kind of the same routine. We need to know the orientation. Is it left, right, up, down? We need to know the center, and we need to know A and B if we're going to graph it. All right. Orientation. X is in the first term, so that means it's opening left and right. Okay. That means then what's below the x, or what's in the denominator there, the first one over a squared. So a squared is 4, so a is 2, which means my transverse axis is going to be 4 units. Okay. That means then that 9 is b squared, so b is 3. My conjugate axis is going to be 6. So here we notice that a squared is less than b squared, okay, which is totally fine in a hyperbola. In an ellipse, a squared is always larger, okay. So we need the center, and the center is going to be, the x-coordinate of the center comes from this binomial involving x, so it's -4. The y-coordinate of the center comes from this binomial involving y, so it's 2. So I'm going to start with the point -4, 2. All right, that's my starting point. From there, I'm going to go, which direction to find the vertices? I'm going to go left and right because of my orientation, and I'm going to go left and right 2 units. So let's come up with the vertices by starting with the center point. So if we're going left and right, we're changing the x-coordinate of the center by adding and subtracting 2. The y-coordinate of the center will remain 2. It's on that same horizontal line. All right, so one of my vertices is -4 plus 2, which is -2, 2. And the other one will be -4 minus 2, which is -6, and the y-coordinate will be 2. So if I plot those points, we should see that they are the same distance from the center. So I have -2, 2, is one of my vertices, and -6, 2. Okay, looks good. All right, now I need to go the other direction. I go the other direction 3 units. I go 3 up, 3 down to find the endpoints of the conjugate axis. So 3 up from the center, 1, 2, 3, and 3 down, 1, 2, 3. Okay, so now I can see that my rectangle is going to have a width of 4 and a height of 6. So I'm going to draw in my rectangle so that it is dashed. Oops, missed. So then I can draw the asymptotes and get some nice looking curves. So I draw my diagonals, making a note of the slope. So from the center to the corner up here, I go up 3, right 2. So my slope is 3/2. Up 3, right 2. So here I'm lucky. I actually know my y-intercept. Okay, so I'm going to go down 3 and left 2 and continue that. So when I write the equation of this asymptote, especially if I put it in slope-intercept form, its slope is going to be 3/2. So I don't know, well, I do know because of my graph, but if we didn't know, we would be able to find it. So we don't rely on the graph for the asymptotes. We saw that from the last example. All right, and then we go and draw our other asymptote. So it has a slope of -3/2. So down 3, right 2. Once again, I got lucky. I hit the y-axis here. Okay, so if I write the other asymptote equation, it's going to be negative 3/2 x, and we know it's going to be minus 4, but we'll show how to find them the other way, which we'll do that as soon as we draw our curves. So now my hyperbola curves open left and right. So basically, the only thing that is part of the hyperbola are the two blue curves. So it looks pretty good. All right, let's come up with those asymptotes without relying on our graph like we did. So the asymptotes, our standard equation is y minus k, the y coordinate of the center. So remember, this is hk. The only point we know on the asymptotes equals the slope, which I'm just going to go ahead and put those in. Oh, actually, let me just fill it in. We already talked about that. So it's y minus 2 equals 3/2. So I could see my slope here is, this is 3, and this is 2. So it happens to be b over a this time. 3/2 times x minus negative 4x plus 4. Okay, so sometimes they like you to leave it like this, and sometimes they have you move the 2 over. So if you're giving your asymptotes in my math lab, they will be okay with you leaving it in one of these two forms. Okay. If we want to get the actual y-intercept, then we need to go ahead and distribute the 3/2. So that becomes 3/2 x. When I take 3/2 times 4, 2 goes into 4 2 times, so that becomes plus 6 plus 2. Aha, here it is. 3/2 x plus 8. That's the one we came up with up here. So the other one, excuse me, then is found by using the negative. So it would be, I'm going to skip to this other version so it's quicker. Negative 3/2 times x plus 4 plus 2. Distribute the negative 3 halves. That becomes negative 6 plus 2, which is y equals negative 3/2 minus 4. 3/2 x. So here's the one with the positive slope, and here's the one with the negative slope. Okay? And last, we don't need the foci to graph, but we're always asked for them because they're part of the definition for for 3 out of the 4 conic sections. So foci, we need C. And so we know, oopsie, I copied this from the wrong one. That should be a plus. C is a squared plus b squared for hyperbola. So c squared is going to be equal to a squared, which is 4, plus b squared, which is 9. So c squared is 13. So c is the square root of 13. So the foci, remember, are located on the transverse axis, just like the vertices. They're farther out. I was going, what, 2 units to get to each vertex from the center. I'm going square root of 3, which is or square root of 13, which is approximately, I forgot. Did I write it down? 3.6 maybe. Okay. So That would be for checking. But what are the exact coordinates of the foci? So we're going left and right. We're changing the x coordinate. So we're taking the x coordinate of the center, which is -4, and we're adding the square root of 13. Will give us one of our focus points, the x coordinate. The y coordinate will be the same. And my other focus point is going to be -4 minus the square root of 13, 2. Okay. So we could come up with a decimal approximation for that. I believe this one right here is approximately 0.4, -0.4. And this one here is approximately -7.6. So we could plot those and make sure we seem like we are equidistant from the center. So -0.42, so it looks like we're about here. And then -7.6 to be here. So looks pretty good. All right, so let's do one more. This is kind of an interesting situation, so I want you to see this. It's got a couple cool things about it. So here's the equation of a hyperbola. How do I know it's a hyperbola? Because in this case, my x squared term is negative. So one of them is positive, one of them is negative. Notice they both have a coefficient of 1. So they can have the same coefficients, but one of them will be positive, one of them will be negative. That just isn't good, so we'll erase that. All right, so let's arrange it so we can put it in standard form. So we're going to rearrange the y terms together, put the x terms together, and move the 2 to the other side by adding. Okay. Now, because the y squared term already has a coefficient of 1, there's no need to factor, okay? So it's just y squared minus 2y. I'm going to add a constant to complete the square. Okay? We still have to be careful with this negative. We still have to factor it out, even though this is a 1. We have to take the negative out. So that's what seems weird when it's a 1. So you don't have to write the 1. I'm just making emphasis there that it is a negative or a -1. So that changes the sign. That becomes positive x squared and positive 4x. I'm dividing out -1 from both of those. Then I'm going to complete the square. Then I will add those, what I added to the left to the right. Okay, so half of 2 is 1, 1 squared is 1. Since I didn't factor anything out, I simply add 1. Okay, here half of 4 is 2, 2 squared is 4, but I did factor something out. I factored a -1, so I have to multiply it by -1, multiply the 4 by -1 before I add. So I'm really adding -4 or subtracting 4. So this one's doubly tricky. Okay, so now factor your perfect square trinomials. This minus, you don't need the 1. It's not wrong if you put it. And then look what I have on the right-hand side. I have -1. 3 minus 4 is -1. Okay, is this in standard form? It is not, because the right-hand side is supposed to be a positive 1. So I need to divide everything by -1. So we've never divided by -1 before, so we have to see that it's changing the sign. So basically now my y squared term is going to be negative, isn't it? So we like to put that one second, so I can rearrange it at the same time. So that will be y minus 1 squared over 1. That negative we'll just put out front. There's that minus. Okay. When I divide here, a negative divided by a negative is a positive. So the expression with the x in it will be first. So it'll be x plus 2 squared over 1 equals 1. So here's a case where why it's doubly interesting is the denominators are the same, but they're both 1. Is it okay if they're both 1? Yes, it is. Okay, in an ellipse, one of those denominators could be a 1. We just don't see it as often, but it totally could. Okay, so here is my hyperbola in standard form. So if I'm going to graph, let's do a quick graph. The center is -2, 1. The orientation is left, right, because the x is first. I know then that a squared is 1, b squared is 1, so a is 1, b is 1, so if you get them mixed up, you're still going to be right. I love that. All right, so let's graph. I don't know why all of our hyperbolas ended up in the same quadrant. Sorry. -2, 1. Here's my center. All right, my center. So basically, to get to the vertices, I go left and right. 1. So I'm going to go left 1, right 1. So I go left 1. Here's a vertex. Right 1. Here's a vertex. So my transverse axis is 2 units wide, but so is my conjugate axis. So when I go the other direction, I go up 1 and I go down 1. So basically I've got a 2 by 2 rectangle, which is technically a square. So when I draw my rectangle, why is that not switching? I draw my rectangle, it's a square. Bad. So my diagonals have a slope of 1. My curves open left and right. So there's my graph. Very fun. I hope you love hyperbolas as much as I do.